Hello, my name is Rick Wasson. My paper is about a new technique for speckle photometry of close binary stars. The goals of this method are to resolve the individual stars within the seeing disk and then estimate their spectral types. One of the fundamental building blocks of astronomy is the mass of stars, and the only way to measure mass is in binary systems. Astrometry can measure the orbit of a resolved binary, or spectroscopy can measure the radial velocities for very close, fast-moving binaries. Distance is also required to know the physical size of the orbit. Now we have excellent distance measurements, especially from the Gaia satellite. Putting astrometry of resolved binaries together with multiband photometry of the individual stars should add new useful information. Speckle interferometry is the leading technique for resolving close visual binary stars. It was invented in 1970 by Labière in France, and it has been used by professional astronomers ever since. Over the last decade, it's also been used by amateurs, now with much better cameras and software than 50 years ago. Speckle is similar to planetary imaging in that we take lots of short images to freeze the seeing. But it's easier than planetary imaging in some ways because you don't have to look for lucky images. And the target is very simple, just two stars. In Speckle, we process all the frames and let the Fourier transform mathematics find the two stars right down to the diffraction limit. So the first goal of this project was to see if we can add photometry to Speckle. Can we actually measure the color index of the two stars? Only a few professionals are doing this, professional teams, and then only for about the last 20 years. If we can measure color index accurately enough, then maybe we can estimate the spectral type of both components, which is actually unknown for most binary stars. The bottom line goal for this project is, can amateurs and students do useful science in this area with small telescopes? The initial speckle photometry work used the FIRO facility of Russ Genet near San Luis Obispo, California. It has a C11 telescope under Dan Gray's SciTech control system, a ZWO CMOS camera with Sloan GRI and Z filters from Astrodon, and it's set up for the right speckle image scale with a Barlow. The observatory control computer is remotely accessed from anywhere over the internet. Amateurs and students have made speckle observations from Texas, Arizona, New Mexico, New Jersey, Florida, Hawaii, California, and probably some other places I don't know about. A little more about Speckle. Florent Lossy, an amateur in France, wrote code for Speckle in 2010. Since 2015, I have used the Speckle toolbox written by Dave Rowe of Planewave Instruments. In 2017, Dave added bispectrum analysis, which is very advanced, to this STB toolbox. Here's an example of what STB can do. We all know about that the atmosphere trashes star images and planetary images. So we take lots of short exposures to freeze the scene. We use a small 256 square pixel region of interest, and we don't guide. It's okay if the star wanders around in the ROI. This example is our first observation, the binary star KR60AB, which is a very nearby pair of red dwarf stars. As you can see, some of the let me move this. Some of the images are lucky and some are really bad. Fourier transform analysis finds spatial frequency information hiding in every one of those short exposures, and then it averages that information into a power spectrum. The Fourier transform of the power spectrum is the autocorrelation. This is not actually an image, but it's a graphical representation which has the correct separation and orientation of the real stars. Bispectrum analysis then reconstructs a real diffraction limited image. There's lots of number crunching going on here. The method untangles the phase of the wavefront distortion in every short exposure. That takes a lot of computer power. Each of the images at the bottom is the resulting bispectrum image from 1,000 frames in one Sloan filter. You can see that the secondary star, which is the fainter and redder of the two red dwarfs, becomes brighter at longer wavelengths, moving left to right. The key to speckle photometry is that once the bispectrum analysis has recovered the correct wavefront phase, it has also recovered the correct flux for each star. The speckle photometry method begins here with aperture photometry of the BSA image in each filter. This plot shows the proportion of flux that comes from each star. The horizontal axis is the filter center wavelength in nanometers. The flux proportions are defined so that the total of both stars is always 100%. 5 sets of observations were made in this case, for a total of 20,000 frames. They have good repeatability except for the cloud, the X points, which were probably caused by a contrail drifting over the star in less than 1 minute, during which the eye filter exposures were being taken, 1,000 frames at 60 milliseconds each. Having the speckle exposures in hand, the next step is to take a few long exposures of the same star in the same camera region of interest and then stack them. The purpose of this is to get a seeing limited blended image with good signal to noise. Then the net fluxes of the A and B stars are scaled up to the level of the high signal to noise long exposures. The A and B star instrumental magnitudes are easy to calculate from their flux. Standard Sloan magnitudes are available in the large survey catalog, such as Sloan Digital Sky Survey, the Pan-STARRS looking for asteroids, and APAS by AVSO for photometric secondary standards. We use mainly the APAS 10 catalog. If there's any smoke and mirrors aspect to this method, this is it. The binary star itself is used as a secondary standard star for self-calibration. The binary is like a comp star in differential photometry of variable stars. The surveys use deep, long exposures, so they have blended, seeing limited stars, just like the unresolved long exposures that we just took. The long exposures are compared with the standard magnitudes from the large survey. The calibration factor shown here is defined simply as the magnitude difference between the survey magnitude and the instrumental magnitude. This calibration factor is a simple shortcut intended to lump together all the photometric corrections. That includes the camera quantum efficiency, the optical train glass that's in the way, the filter transformations, and all the atmospheric corrections from extinction. So it is updated often. In fact, every Speckle data point, which consists of 1,000 Speckle frames, is recalibrated with several long exposures. To get standard magnitudes for the components, the major assumption is this: the calibration factor, which was derived from the unresolved images, can also be applied to the individual A and B stars from these bispectrum analysis. We just add the calibration factor back to the instrumental magnitude of the A and B stars. Here are the resulting magnitudes of the individual components. The blue is the top is the primary, the red dash is the secondary. Color index is simply the magnitude difference between any two filters. For observations in 4 filters, there are 6 combinations for each star. The pioneers Johnson in photometry and Morgan in spectroscopy joined forces in 1953 to establish the correlation of photometric color indexes with spectral type. Johnson started with UBV photometry, so he got 2 color indexes, U minus B and B minus V. Better detectors expanded the correlation to Johnson-Cousins photometry and later farther into the infrared. In this work, we used the data from Mamajek's website at the University of Rochester, covering all main sequence spectral types from B through M. Since we used Sloan filters, it was also necessary to use well-established transformations from Johnson-Cousins to Sloan. These are the 6 Sloan color index correlations with spectral type for main sequence stars. At the bottom is an integer parameter for each letter and number spectral type used for interpolation. It goes from 0 to 59, corresponding to spectral types B0 to M9. Here's an example of the color index correlation for the primary component of our binary star KR60AB. You can see that these arrows are color coded and they point down to their color index line. The pink line goes down to here. Yellow line intersects here. The red intersects here. The blue is over here. The dashed orange is down here, and the black line, the largest color index, because it's the widest apart filters, G minus Z, is way down there. You can see the G minus Z is almost 3.5 magnitudes different. All 6 arrows line up fairly well with spectral at the same spectral type. Some of them fall nearly on top of each other. In summary, this table shows the individual color indexes that were measured for the A and B stars and their corresponding interpolated spectral types. In the blue boxes, the weighted average of all those 6 values is M2.8, corresponding to the Washington Double Star Catalog, WDS. It gives M3.5, not too far off. The corresponding spectral type for the secondary star is M5.2, and the WDS gives 4.5. This is the summary of all of the 4 stars that we observed in this exploratory study. covering spectral types A, F, G, K, and M. There are reasonably good matches between the Speckle photometry results and the WDS catalog. For example, the spread of 3 nights for KR60 was 2.8, M3.0, and M2.9, pretty tight, corresponding to M3.5 given in the WDS. And corresponding spectral types for the secondary star. A3.1 versus A0, A8.8 quite a bit later versus A3 for the secondary given in the WDS catalog. Almost exactly the same value for the primary of this K-type binary. And then this one is a little bit later than the K1 in the catalog. And early type F1 corresponding to F0 and G1 corresponding to G0. But this one is quite a bit later. So there's 2 or 3 digital spectral type differences there. In conclusion, one thing I didn't show was the messy hash that can appear on non-photometric nights. We observed on several poor nights that started out well, but then the marine layer rolled in from the Pacific Ocean. And the lesson learned is don't bother with non-photometric nights. We found that the STB does distribute the A and B flux pretty well, and repeatably. The self-calibration method gives approximate but reasonable standard magnitudes and color indexes. The color indexes can be measured accurately enough to predict consistent spectral types, and the A and B spectral types match the WDS fairly well. The bottom line is the Speckle photometry scheme seems to work, and I don't think anyone else was as surprised as I was. Thank you.